Okay, so today is going to be quite a bit of me talking and you listening. It's unfortunate, but sometimes when we got to make sure we get through stuff, that's the way it's going to be. That said, there is quite a bit of important information in this lesson. Not so much about recall, like not so much memorizing it, but a lot of it is you're going to be asked to apply it, okay, in questions on this particular unit exam, possibly on the final exam. Okay, we're going to talk about things like heat transfer. Okay, how does heat get transferred from one thing to another? So that has a little bit to do with the second law of thermodynamics, but more in this unit, we're going to be looking more at how can we either improve the transfer or how can we prevent the transfer. Okay, if we're preventing the transfer of heat, what's another name for that? What are you doing if you're preventing heat transfer? You're insulating. Okay, so we're going to be talking about kind of practical applications. How do we insulate something, or how do we increase the absorption of something, things like that. Okay, so we're looking at practical applications of kind of those ideas. We're also going to look at how energy on a global scale gets transferred from place to place. Now, as a quick review, the main or most important factor that affects climate for any place is what? Latitude. Okay, how close to the equator you are. So obviously the equator gets more energy than any other place on Earth. But somehow it's got to get other places. Okay? How does energy typically get from places that are warm on Earth to places that are colder on Earth? How does that energy move? Yeah, wind. Okay? Wind currents make the energy move because the second law of thermodynamics says energy has to flow from hot to cold. That means it's got to go from the equator to the poles. Now, does it always get there? No. Okay, it gets lost along the way or transferred out along the way. That's why the poles are colder than the equator is. But okay, we're going to be looking at kind of the mechanisms of that, right? Most important thing, we're going to be looking at the three methods of heat transfer. The three methods of heat transfer are conduction, convection, and radiation. Okay? Those are the three ways that heat can be transferred from one place to another. Okay? Conduction works mostly in solid materials. Okay? It's that whole atomic particle theory, okay, where when something gets heated up, its particles move faster and they run into each other more often. Well, in solids, because the particles are really close together, they can run into each other really easily. Okay, so heat is transferred in solids generally by them conducting it, that is, slamming into one another and transferring the energy from one particle to the next. Okay, convection occurs in fluids. That could be liquids or gases. Okay? And it's currents. Hot air rises, cool air descends. That's an example of a convection current. Okay, so that's what convection does. If you have a convection oven, okay, at home, it has a fan inside that circulates the air and makes sure that all parts of the oven have about the same temperature. If you don't have a convection oven, obviously the parts closest to the element that heats it up are going to be hotter. Okay? And then lastly, radiation. Okay, not the kind that turns you into some sort of shape-shifting blade having out of the back of your hand kind of thing. That's all fake, obviously. Okay, radiation is any form of energy that travels by waves. All right, so heat energy travels by waves, light energy travels by waves, those kinds of things. All right. So they're all important, but they all have different roles to play. They're all important at different times. Okay, that's where we're going to kind of be looking at. All right, so the things we're going to look at. The three parts of the Earth, understand how energy on Earth is absorbed, used, and reflected, okay, and understand how the energy and the Earth interact to produce the conditions necessary to support life. Okay, so energy, when it strikes the Earth, first up, where does the energy come from? The sun. Okay, so energy that comes to the Earth comes from the sun. It's a form of essentially solar energy. Okay, it's radiation. It's coming from the sun, and it's striking the Earth. Okay, three things can happen to that light when it strikes the Earth. What does a lot of it do? A lot of it reflects. Okay, now how much of it reflects is a factor of what the surface it hits is like. Okay, what's a highly reflective surface that might be present on Earth? Okay, the ocean actually is quite absorptive. Actually, I mean, we always say, oh, I can see my reflection in it, but it reflects certain wavelengths of light, but it actually absorbs others. That's why it gets darker the further down you go. Yes, some does reflect off of it, but there's one really reflective material that sometimes covers certain parts of snow. Yeah. Snow is white. Anything that's white reflects all colors. Okay, so if you got an area that's covered with snow, a lot of the light is being reflected away, and not much of it is being absorbed. Okay, so essentially, three things can happen: it can be absorbed, it can be reflected, or it can be used. Now, we're talking natural conditions here, not Drake Landing solar panel kind of used. Okay, we're talking about things that in a natural environment can directly use the sunlight. What things can do that? Plants. By what process? Photosynthesis. So we sometimes, instead of using the word used, we sometimes say converted. Okay? And we mean converted by photosynthesis. Okay? That's really those are really the only three things that can happen to light energy from the sun when it arrives at the Earth. It's going to be reflected, or it's going to be absorbed, or some of both. Okay? Or it's going to be converted into chemical energy by plants. All right, making sense so far? Okay. Now, the atmosphere is the first thing that this radiant energy from the sun is going to strike. Okay, it's that surprisingly thin blanket of gases, okay, that surrounds the Earth. Right? Obviously, it has different layers. The layer that we live in is the troposphere. I'm never going to ask you about the names of the layers of the atmosphere. All right, but we live in the troposphere. It's the most dense part because it's closest to the Earth. Okay? Gravity pulls the atmosphere down, and so this is where the good gases are, let's say. Okay? So this is where we've got, you know, our nitrogen-oxygen mix that makes life so important. The higher up you go, the thinner the atmosphere becomes, right? Which is why generally temperature decreases with altitude, right? It was one of the factors that affects climate is your altitude, about 6.5 degrees for every 1,000 meters. Okay, the thinner the air gets, the less able it is to retain heat. Now, the higher up you go, obviously, the concentration of the gases that we require becomes less and less and less. Okay, the troposphere where we live, okay, extends to around, okay, 11 kilometers or 11,000 meters, around 30,000 feet, 33,000 feet, okay, somewhere in there. Even if you were standing on Mount Everest, you would be at the upper reaches of the troposphere. Can you live there? Can you survive there for a short period of time? That's the key. Okay, you can survive there for a short period of time, but you cannot live up there. Okay, not on the top of Mount Everest anyway. The air is simply too thin. Okay? Your body is slowly dying if you live up there. Once you are up there. Okay, climbers call it the death zone, and that's a really ominous name, but it's an accurate name too. Okay, when you get above a certain altitude, the pressure of the gases is not sufficient to keep you alive. Okay, you start losing water really rapidly. Okay, water evaporates more quickly. Okay, and as a result of not having very much pressure, fluids don't stay in your bloodstream. Okay, they turn into gases and they try and bubble out. Okay, and you can get fluid building up in your lungs. You can get bubbles in your bloodstream. Okay, and things like that. Now, bubbles in your bloodstream, good or bad? Very bad. Okay, if you get bubbles in your bloodstream, they can create stress on the small blood vessels called capillaries. In fact, they can lodge in them and block them. Okay, if that happens, pressure builds up behind. Okay, and then you can have an aneurysm, which is a broken blood vessel. Okay, if that happens in your brain, it can be very serious. Okay, if it happens in your lungs, then you can start getting blood in your lungs and you can drown. Okay, without actually being underwater. Right, so these are pretty serious things. It's important that we stay down in this area where the pressure of the gases above us is normal. Okay, that's why if you take your suit off, your space suit off in space, you pop. Okay, because there's no pressure anymore. Okay, and all the gases that are normally dissolved in your blood turn back into gases, and they get bigger and bigger until you. Yeah, it would not be a good way to go. Explosive decompression. It's got to be right up on my list with ways I don't want to die. Probably right underneath inhaling molten rock. Yeah. in outer space. Unfortunately, there was some research done on that back during the space race. And the animals that they tested survived for around a minute. Yeah, and that would be a pretty long minute. Yeah, it's not a pleasant thing. You might not be conscious the entire minute, but yeah, it would take at least a minute, maybe a little bit more. Yeah, but it would be really unpleasant. Okay, I mean, just if you've ever had a muscle cramp, okay, you know how kind of acutely painful that can be. Well, imagine that multiplied by about 100 times everywhere. Okay, not just that one muscle, but kind of everywhere. It would be, yeah, it's not pleasant. It's like the bends. Anyone ever heard of the bends? Divers get it if they come back up from deep too quickly. Okay, well, it's the same idea. More of the gases can dissolve in your blood the deeper down you go because there's more pressure. If you come up too quickly, they'll bubble out of your blood and lodge in your muscles, and it's really painful, and you have to get put in the big tank. Okay, the hyperbaric chamber, where they increase the pressure, force that stuff back down so that it's not a gas anymore into your blood, and then slowly release the pressure. Okay, so that stuff can come out at a proper rate and not be painful. So yeah, it's pretty serious. Okay, the atmosphere plays an important role, at least in that way, for pressure-wise for us. Okay, it also uses some of the upper layers to protect us from some of the harmful stuff that comes from the sun. Okay, not everything that comes from the sun is good. Right? A lot of it is. Visible light is good. Heat is good. Okay? Even to some extent, ultraviolet light is okay as long as there's not too much of it. Okay? But the upper parts of the atmosphere, they scatter and reflect the shortwave radiation that comes from the sun that's really harmful to us. X-rays, gamma rays, so we don't turn into the Hulk, things like that. Okay? Not that that would actually happen. But, yeah, that kind of stuff gets turned away very early on. Okay? So it doesn't reach the surface here. Okay, so stratosphere is a little bit higher up than that. Okay, that's essentially where commercial jetliners and things like that, they would fly in the stratosphere. Okay, there's special winds that go on up there called the jet stream. Okay, I don't know if anyone watches the weather or anything, but they usually talk about the jet stream on the weather. It's a high altitude wind that transfers energy. Okay, ozone gas is present in the stratosphere, and ozone obviously is the layer of the atmosphere that protects us from ultraviolet light. Okay, it reflects it essentially. If we get holes in the ozone layer, then more ultraviolet light can come pouring through. Okay, yeah, you'll get a better tan, but in the long run, it's not all that good for you. Okay, we did have back in like the early 90s, late 80s, really bad holes in the ozone layer. Okay, people didn't realize what was causing it, but it was actually propellants from aerosol cans and things like that that were contained chlorinated fluorocarbons, CFCs, and they could destroy ozone, and they were essentially killing the ozone layer, and lots of UV light was getting through. The biggest hole was over Australia. Australia coincidentally has the highest incidence of skin cancer of any country in the world. Okay, partially because of that, and partially because of the lifestyle in Australia too. They like to spend time on the beach, they like to spend time outside. That's just a cultural thing for them. Okay, all right, is that making sense? So the atmosphere's got a lot of roles, but its most important role is to absorb and transfer the energy received from the sun, because the other parts of the Earth can't do it. Okay? The atmosphere is the most fluid of the three parts of the Earth. The three parts of the Earth being the atmosphere, the lithosphere, which is all the rock and solid parts of the Earth, and the hydrosphere, okay? All of the liquid water parts of the Earth. Okay, it's the most fluid. It's the kind that most, or the part of it that most easily moves and transfers around. Okay, wind essentially. All right, so it plays a critical role in maintaining the Earth's temperature, which in turn has a profound effect on the Earth's climate. Okay, how many of you have heard of the greenhouse effect? Okay, and you've probably heard that it's bad, right? It's not. If it increases a lot really quickly, that's bad. But without the greenhouse effect, Earth would be really cold. Okay, we need a certain amount of greenhouse gas in the atmosphere to retain heat for the Earth. Otherwise, it would just go right back off into space, right? So having some greenhouse gas is important. Is the rate we're putting it into the atmosphere good? No. Okay, but the greenhouse effect in and of itself isn't bad. Okay, a drastic increase in it is bad. Okay, but the greenhouse effect isn't all bad. Right, so when when heat comes into the atmosphere, okay, some of it gets reflected because clouds are white. The tops of clouds are white, right? So they're highly reflective. So some stuff reflects off of there, okay, and some of it gets scattered. Okay, now that's why the sky is blue, because the makeup of our atmosphere, the gases that are in it, tend to scatter shorter waves of light. Shorter waves like X-rays, gamma rays, ultraviolet rays, and violet or blue light. Okay? So when light strikes the atmosphere, it gets scattered around and makes the atmosphere look blue. Okay? Everyone follow me there? It's not because the sun reflects off of the ocean. I know someone somewhere along the way has been telling you that. Okay? The last time I checked, the ocean is made of water. What color is water? It's clear. Okay? The ocean looks blue because it reflects the sky, not the other way around. Okay? So, I know, but you believed it your whole life, right? Oh, the sky is blue because it reflects off the ocean. The ocean's blue. No, it's not. The ocean is clear. Okay? It's made of water, which is clear. Now, you'll sometimes notice, though, at sunset, the sky isn't blue. It's red, orange, yellow. Okay? That's because when the sun gets low on the horizon, okay, the sun's light is now traveling through particulates, pollution and things like that, okay, that are nearer to the Earth's surface. Well, they scatter different wavelengths of light. They scatter the oranges and the reds, okay, and the kind of browns and things like that. Like this summer we had the forest fires, right? Okay, we had all that smoke in the air. Well, the sky wasn't as blue as it normally is. It was kind of a grayish brown some of the time. Sometimes when you drive towards Calgary, you can see that brown layer, okay, sitting over the city. It's pretty gross actually, but okay, you can see that there, and that's the particulates, the pollution that's in the air, okay, and it scatters light differently, so it appears a different color. Everyone follow? All right, so a lot of the sun's radiation gets turned away long before it reaches the Earth's surface. Now, is it important that the atmosphere absorb some of that light? Yeah, because we want the temperature to go up. If we absorb energy, temperature goes up. So the atmosphere does absorb some, okay, and some of it gets through and strikes the Earth's surface, at which time some of it's going to get reflected and some of it will be absorbed, and that will increase the temperature of the Earth's surface, or if it strikes the ocean, it'll increase the temperature of the ocean. Okay, everyone follow me there? Okay, the reflected light can do two things. It can go straight back out into space, or it can hit the greenhouse layer or the bottom of clouds and reflect back down. Okay, the more times it reflects back down, the more heat is retained. Right? It's the same thing that makes your car get really hot on a sunny day. Okay, light can come in through the windows. When it strikes the interior of your car, it changes its wavelength a little bit, makes it a little bit longer. Okay, and when it tries to go back out, it can't, because the windows can reflect that wavelength of light, and so it just keeps going back, and it just keeps reflecting back and forth inside your car, and more of it ends up getting absorbed, and then as a result, your car gets hot inside. Okay? Now, are there certain colors that absorb more energy than others? We already said white is highly reflective, so what's going to absorb a lot? Black. Okay? Black essentially absorbs all light. Okay? Now, that said, if something was truly black, you wouldn't be able to see it, because it would absorb all the light and not reflect any. Okay, everyone follow me there? Like a black hole, you can't really see a black hole, right? You can, theoretically, right? You couldn't see it because it's so black that nothing escapes from it. All you can see is the void it creates when it moves in front of other things. That's how they track and discover them, okay? Is that suddenly stars disappear for a second and then they reappear, okay? Because something moves in front of them that's completely black, okay? Now, if you're absorbing lots and lots of light, you get hotter and hotter and hotter. Right? If you got two identical cars outside on a hot day, one of them is white and one of them is black, okay, you can probably put your hand on the white car, okay, but you probably can't hold your hand on the black car very long. Okay? It gets hot a lot faster. Same with interior colors. Lighter interiors will stay cooler. All right, so that's what we see here. Okay, we're talking about this term right here, albedo. Okay, refers to the reflectivity of the Earth's surface, okay, or of an object. In the summertime, we don't have any snow, usually, okay? And so the surface of the Earth around here is darker, okay? It's green, or, you know, if we're looking at bare Earth, it's brown to black, okay, and it can absorb a lot of energy. In the wintertime, we're covered in snow and a lot of the energy goes away, okay? A huge difference in the absorbed amount of light between winter and summer, okay? In the summertime, about 70% of the incoming solar radiation that gets through the atmosphere can be absorbed, because we're talking about darker colors being exposed to the sun, okay? About 10% gets reflected off of water, okay? And about 20% gets reflected off of the Earth's surface, even if it is a darker color. In the wintertime, because we have white covering with snow, 85 to 90% of the incoming light gets reflected away. Okay? And that's why it can remain cold as long as snow cover persists. Okay? Now, what do we do to try and get rid of snow, especially if it's on the road? Okay? Sometimes we put salt on it. Okay? So we put salt on it because that lowers the melting point of the raises the melting point of the snow. Okay? Helps it to melt at a lower temperature. We don't just throw salt on it though, we throw something else too. So yeah, sand and gravel and things like that. Why do we throw the gravel on? Actually, it has two reasons. Yeah. Right. One, for traction. Two, it raises the albedo, lowers the albedo, okay, of the surface. That is, it makes it more absorptive. Okay. Low albedo means absorbs a lot. High albedo means reflects a lot. Okay. So by putting a dark substance like sand onto the roads, we lower their albedo, we increase the amount of energy they can absorb, and in combination with the salt we put on the road, we can get the ice and snow to melt on the road even if the air temperature is like -8. Okay, sometimes even -10. You've probably noticed that. Okay, sometimes it's well below zero outside, but the roads are wet because the snow on them is actually melting, even though the air temperature says it shouldn't be. Okay, that's because we're assisting in that. Okay, it's also why our roads are dark in color. Okay, we want to have dark colored surfaces, black. Okay, because that helps to absorb more energy. Okay, if you go to California, they don't build their highways and stuff out of pavement like we do. What do they use instead? They use cement. They build theirs out of concrete because it's a lighter color. Okay? I know when I was a kid, they didn't do that. We went down to Disneyland, drove down, and we got a flat tire in our truck. Okay? And when my dad went to jack the truck up to take the wheel off, the jack sank into the pavement. Okay? Because it got that hot. Okay? It got so hot that the pavement actually got soft. Okay? And we get that sometimes here too. When heavy trucks drive on warm roads, they create the ruts, okay, in the middle, okay, where their tires typically go. And that's why we have to resurface them occasionally. Okay, making sense. All right, so just a quick thing to remember here, okay? You might want to write this down if you didn't already. High albedo, very reflective. Okay, just in case it's counterintuitive for you. Okay, low albedo means very absorptive. That's missing an R. Absorptive. Okay. So is albedo something I'll probably ask you about? Yes. Okay. Have we gone over a bunch of practical applications already? Okay. And this all has to do with one method of heat transfer. That's radiation, the incoming light that's coming into the Earth. All right. Okay, so gases present in the Earth's atmosphere, okay, help maintain the Earth's temperature and climate. Okay, we got CO2s, CFCs, methane, ozone, nitrous oxide. They allow the incoming radiation to get through, but these are our greenhouse gases. They don't allow it to go back out. So it comes in, as you can see in this diagram here, and then it reflects off. Okay, some of it gets out into space, some of it hits the Earth's greenhouse gases and reflects back down. The more of it that does that, obviously the more trapped heat we have. Okay, Earth has kind of a nice balance on that. Right? Is there an example somewhere that we've seen of a greenhouse effect that might be out of control? No. I'll give you a hint, it's not on Earth. Is there a planet in our solar system that has a really out of control greenhouse effect? Venus, yeah. Okay? Venus has an incredibly out of control greenhouse effect. Its entire atmosphere, which is about 100 times thicker than ours, is carbon dioxide. Okay? And it basically lets no light back out. Once the light gets through the cloud layer, okay, it gets trapped and just keeps going back and forth, back and forth. As a result, the temperature on the surface of Venus is several hundred degrees Celsius. Okay? Any probes that land there last about 45 minutes to an hour before they melt completely. Okay? The Russians had a whole bunch of probes that they sent there back in the 80s to take pictures of the surface of Venus. Okay? And the longest that any one of them lasted was just over an hour. Okay? Yeah. Okay? So really runaway greenhouse effect. Not nearly that bad here. All right? Okay, sorry, this picture here, I found it just the other day. It was about rain. It actually has nothing to do with this. It's about rain shadows. Okay, and we talked about that rain shadow effect and factors that affect climate, presence of mountain barriers. Okay, you can see here, this is Mount Robson, and this happens on Mount Robson all the time. Okay, you have warm, moist air masses that move in kind of from over here, and the air is clear. You don't notice that they're there until they hit the mountain and they get forced up over it. And as they get forced up over it, all of a sudden this cloud will appear out of nowhere. Right? This cloud appears out of nowhere as that air mass tries to climb up the side of the mountain. Okay? Then for about an hour, the mountain will be shrouded in cloud, and then the cloud thins as it gets over the top. You can kind of see here that it's kind of spinning and thinning out. Okay? And then suddenly it'll be gone, and there'll be this fresh layer of snow on the top of the mountain, even though everywhere else it was clear and blue. Right? That's the rain shadow effect. If you have a huge air mass and it runs over the top of high mountains, it's going to lose a lot of its moisture here and then be dry over here. All right? Everyone all right with that? Okay. Okay, hydrosphere. So that's the role of the atmosphere in capturing energy. Okay? So the hydrosphere includes all the water on, above, and under the Earth's surface. Okay, we have lots of aquifers, and if you have a well, you tap an aquifer. That's underground water. Okay, is known as the hydrosphere. That can be water vapor, liquid water, and ice. Okay, less than 0.1% of all the water evaporated from the surface of the Earth is returned to lakes, rivers, or streams, or seeps into underground hollows. The rest returns to the ocean, or is frozen in ice caps. Okay, so if water evaporates from here off the ground, it's not falling back here as rain. Okay? It's going to fall as rain somewhere, but it's not going to fall back here. Why? Why can't it just go straight up and come straight back down? Yeah, wind is always moving the atmosphere around. Okay? So the air that's here right now isn't going to be here 10 minutes from now. Okay? It's going to move around. It's going to constantly be going places, so it's not going to stick around. That, and when rain hits the Earth's surface, gravity takes over. Yes, some of it gets absorbed into the soil, but a lot of it just runs off and goes into rivers. And where do the rivers all go? To the ocean. Right? So a lot of that stuff ends up in there. Okay? If it didn't end up in rivers, all the rivers would dry up. Okay? So a lot of it ends up there. Okay. So, water cycle. How many times have you seen this in your life? A bunch of times. Right? Okay, one more time. Okay, you knew all the parts of it, probably. Okay, so we've got how water essentially gets into the cycle is that it has to evaporate from either a liquid water body, ocean, river, lake, whatever, or it needs to be evaporated from the surface of plants through what's called transpiration. Okay, sometimes it's called evapotranspiration, but transpiration will do. Okay, that's plants losing water as they carry out photosynthesis. Either way results in water vapor now being present in the atmosphere. As that water vapor goes up, it cools, it condenses, okay, and it falls as precipitation. That could be snow, it could be rain, it could be hail, okay, whatever the case may be. Now, once it starts to fall back to Earth, several things can happen to it. The most common thing that can happen to it is it runs off, okay, ends up in rivers and it heads to the ocean. Sometimes, though, it falls as snow and gets trapped, okay, in what we call freshwater storage. Glaciers. Okay? Glaciers, ice caps, things like that are freshwater storage. That fresh water could be stored in that body of ice for thousands of years. Right now, that's not likely because the glaciers everywhere are shrinking. Okay? But if you go back, let's say even 5,000 years, there was a very large sheet of ice covering the majority of North America, okay, called the Laurentide ice sheet. Okay, go back 10,000 years, that sheet of ice covered the entire North American continent and was 1 kilometer thick. All right, so if you were here, standing right here, 10,000 years ago, you'd be under a kilometer of ice. That'd be cold and heavy, by the way. Okay, that's how the big rock got out where it is. Right? You guys have all been out to the big rock, yeah? Okay, the big rock was actually pushed off of a mountain near Jasper by a glacier, pushed outwards, and then dropped. When the glacier receded, it was dragged backwards, and then a piece of that glacier broke off, and nothing could pull on that rock anymore, and left it there. Okay, that's how it ended up there. That's why it's called the erratic. It's made of an entirely different kind of rock than is present around here. Okay, so all of that can happen as freshwater storage in the form of ice. You can get freshwater storage in the form of lakes, ponds, sloughs, things like that. Water that stays in one place for a while. Okay, or it can, by this process, infiltration, penetrate into the soil. That is where it gets absorbed, okay, and it's held in the soil, or maybe absorbs far enough that it becomes groundwater. Okay, that would be aquifers that we would access with wells. Okay? It's where the majority of drinking water usually comes from. Okay, even Okotoks, a lot of our drinking water doesn't come from the river. It comes from wells that are recharged by the river. Okay. All right. Any of that stuff that gets stored is kind of out of the cycle for a little while, especially if it's in ice or underground. Okay, the rest of it runs off, goes back to the ocean, and starts in the cycle again. Okay, so the processes we're worried about: evaporation, precipitation, runoff, and infiltration. Okay, those are the big ones. I usually have a diagram of the water cycle on the exam in the multiple choice. Okay, just so you know, those are pretty easy questions we should all get right. Okay, so for the hydrosphere, just some numbers for you here. 97% of all the Earth's water is saline. Okay, that is, it is salty, it is in the oceans. Right? Less than 3% is fresh water. Right? And unfortunately, 3/4 of that 3% is frozen. Okay, in ice caps and things like that. Right? So there's actually very little fresh water on the Earth's surface. Okay? Something that's pretty important to all of us, as we can't use salt water for drinking. Okay? So it's a pretty valuable resource, okay, when you think about all of that. Are we pretty fortunate here in Canada for fresh water supplies? Yeah, we got to take care of them though, right? The supply of our fresh water comes from glaciers and ice sheets, and we know that those are always getting smaller. All right, so examples here. Obviously, this is where 97% of the water is. Okay, we've got rivers and lakes. Okay, but those are supplied by these. Okay, this is a glacier here on the right-hand side. Okay, this is the Robson Glacier that comes off of Mount Robson, and it is shrinking rapidly. They had a when we did this hike, there was a sign out in this meadow, and it said on it, in 1901, the Alpine Club of Canada marked this spot as the toe of the Robson Glacier. My dad and I were standing there looking at the sign going, you see a glacier? We walked a kilometer, then we got to the glacier. Okay, it had receded in 100 years a kilometer. Okay, and that's not just recede back this way, that's also shrink. Okay, it was probably a lot higher in the valley when it was a lot longer too. So we're representing here pretty major loss of water. And as the temperature of the Earth goes up, obviously those don't grow anymore. Okay. Right, other place, groundwater, and that's when water can infiltrate down into these underground wells and aquifers and things like that. How do those get recharged? How does an aquifer get recharged or filled back up with water? Wetlands. Wetlands are really important for recharging water. And so if you got a slough, okay, or a pond or something like that, those are recharging your aquifers and your groundwater. Okay? If we allow those to dry up or we develop over top of them, we remove areas where groundwater can be recharged because water's not going to be absorbed. Okay? In the concrete jungle, okay, there's no absorption. Okay? If you're in Okotoks, the only places where water realistically gets absorbed is maybe in people's yards. Okay, but a lot of that just runs off too because people's yards are typically graded, so water runs away from their homes. And then it gets onto the street, runs into the gutters, goes straight into the river, doesn't get absorbed. Okay, so yeah, it's something to be concerned about anyway. Okay, so for the hydrosphere, can a lot of heat energy be stored here in the ocean? Yeah, the ocean can absorb a lot of energy. And we said proximity to ocean is a factor that affects climate. Agreed? Okay, and that's because there's a lot of energy here. And if I live next to the ocean and the air temperature drops below the temperature of the water, the second law of thermodynamics says that energy flows from the ocean to the air and keeps the air warm. That's why living near an ocean can affect your climate. Okay? It's a major source of energy, and it can regulate or make your climate a bit more mild. Okay, and the lithosphere, so all the rock and solid parts of the Earth's surface. Okay, a lot of energy gets absorbed here, but there's very little transfer. Okay, energy can't flow through the Earth's crust very well, which is good because I hear that like below the Earth's crust is quite hot. Yeah, like the mantle and the core, they're pretty hot places. Thankfully, energy doesn't flow from them outwards very much. Okay, otherwise it would be a lot hotter here on the surface. Okay, so we don't get a lot of heat transfer. If a lot of heat energy hits the Earth's crust at the equator, I'm not going to have that transferring up here, not through the solid part of the Earth. It's going to transfer more with wind through the atmosphere, through the fluid parts. Energy transfer happens way better in the atmosphere, a little bit better. Sorry, it's best in the atmosphere. It's reasonable in the ocean because the ocean is still fluid. Okay, but the Earth's crust plays very little, plays a very small part in the transfer of energy from one place to another because it all happens by conduction. Okay, and that is the contact transfer from one particle to the next. All right, it would be like trying to move water by a fire brigade method for like 5 kilometers. Okay, you guys know what I mean by fire brigade? The buckets, right? Someone is near the lake, they fill the bucket and they pass it to the next person, and they pass it to the next person. It's not a very effective way to move water. Okay, it's not very fast. All right, so that's kind of what conduction is like. It's a very slow way to move energy from one place to another, and it's pretty inefficient. If you've ever watched a bucket brigade, a lot of water gets spilt as the bucket gets passed along. Well, it's the same with heat energy. Okay, a lot of the energy gets lost and dissipated along the way. So very little energy transfer happens here. Okay, the important part of the lithosphere is soil. Soil absorbs a lot of energy, and soil is where plants grow. Without soil, there's no plants. Plants are the only thing that can convert solar energy into chemical energy, so without soil, there's no life. Okay, we got to have something in which plants can grow. All right? Now, looking at that picture, does that look like soil? Pretty rocky, right? I mean, you probably wouldn't want your garden to look like that. Okay, but it's still soil. Something's growing in it. Okay, soil is very different from place to place. Okay, here our soils are kind of sandy. Okay, if you go up more by Red Deer and Edmonton, they're a lot finer and a lot darker. Okay, so soil is made up of different things, and the reason soil is made up differently is it comes from rock. Soil is built by the decomposition and breakdown and weathering of rock. So whatever your rocks are like, that's going to determine what your soil is like. How many people have been to Prince Edward Island? Anyone been out to Prince Edward Island? Okay, what color is the dirt? A lot of it is red, okay? Because the earth around there is made of this kind of red clay. Okay? And as that red clay and stuff kind of breaks down, it makes red soil. Okay? One of the big tourist traps is that you can buy a PEI dirt shirt. They take a white shirt and they just put it in mud, and it's got all this red stuff in it that essentially dyes it kind of an orangey brown color. I don't know, people buy them. It says PEI dirt shirt on it, but yeah. Okay, but it's made of different kinds of rocks, so you get different kinds of soil. That's kind of the point there. All right. How many of you dug a hole as a kid? Okay, good. What did you notice as you dug the hole? It got more difficult, yep, okay? Because once you got through kind of the soft, soily part, you usually hit, okay, probably, hopefully before you hit rock, you hit some clay, yeah, okay? Typically, guys, soil is divided up into what we call horizons or layers, okay? The top layer is the topsoil. Okay, that's where all the nutrients are. It's the part the plants want to grow in. Below that is kind of the clayish layer that we call the B horizon. Okay, there's not a lot of organic material in there, and it holds and seals moisture in pretty well. Okay, below that is what we call the C horizon. That's the parent material, or the rock, okay, that all of the other parts of the soil came from. Now, why do you suppose? It doesn't really matter where you go, but why do you suppose anywhere you go, you can dig down a little ways and always hit clay? Why is clay always under the other kind of soil? Well, I mean, clay naturally retains water because of its structure. Okay? But why does clay always end up underneath? Why isn't it on the surface? Sort of. You're on the right track. If you ever feel dirt between your fingers, all dirt feels different. Okay? If you take topsoil tends to be kind of gritty, especially around here because it's got a lot of sand in it. Right? Below that layer is your clay, and if you put clay between your fingers, it feels more like flour. It's very fine, almost smooth and slippery. Okay? Because its particles are very small. The particles of soil, the topsoil above, are bigger. And so what you end up getting is near the surface, big particles. Okay, kind of like this. This is like magnified greatly. Okay, and when water comes along and kind of moves across the surface, it's always got stuff in it. Fine particles like clay, which are very small, can wash down through the top layer, and they collect underneath. So you get this layer of really, really fine stuff that's very tightly packed because it's so fine, okay, building up underneath. In your sandbox, if you had a sandbox as a kid, okay, there's always clay underneath. Now, take it from me, I'm a person who built a sandbox for my kids. I did not put any clay in the sandbox, okay? But after a couple of years, there's clay at the bottom of the sandbox, right? As dust and things like that blow things around, they land on the sandbox, water gets in there, it washes the fine silt into the sandbox, and it washes through the sand and ends up underneath. Collecting underneath is a layer of sand, of clay. Okay, so that's why clay is always underneath. It's finer and it gets trapped underneath. Okay, and then like we said, below that you've got your rock. Okay, around here is the rock pretty close to the surface. It depends where you are. Okay, I know where my house is. It's really close to the surface because when I tried to build my fence, I got about that far. Okay, and then I hit rock. I'm like, oh, I hit some chunk of concrete or something. Nope, didn't matter. I drilled holes with the auger all around in that area. This far. Okay. Yeah, it all depends where you are. Okay, in some places in town, you can probably dig a little bit further. Okay, but in other places, the sandstone that is the parent material for all of our soil here is actually quite close to the surface because we're quite close to the mountains. It takes a long time for soil to build up. Okay, and once that big ice sheet I was talking about before receded, okay, when an ice sheet moves away, it scrapes everything clean, okay, and leaves behind bare rock. If you've ever been in the mountains, you can see where glaciers have been. They just wear it right smooth and break it off, and there's nothing but bare rock. Okay? It takes a long time for silt and things like that to deposit and build up and make soil. That's why the higher up the mountain you go, less and less grows. It's not just about temperature, it's about depth of soil. Okay? So our soil is relatively young, maybe only a few thousand years old. Okay? Whereas if you go further east, okay, to lower altitudes and lower latitudes and things like that, you're going to have thicker, older soil because they've been free of ice for a longer period of time. All right, so things you'll need to remember. A, B, and C horizons. What's in each one? Okay, A horizon is topsoil. B horizon is subsoil, clay. Okay, C horizon, rock. Okay, again, this is also why the lithosphere has a very small part to play in transferring energy. Energy just does not flow through solid materials very well over large distances. Okay, I'm going to give you a 2-minute break because I've been talking steady since we started. I'm going to give you a 2-minute break, okay, and then we're going to keep going. All right, so again, looking kind of quickly at those three horizons of the soil we're most concerned with. The A horizon is the topsoil. Okay, typically in prairie soils, the A horizon is quite thick. All right, the reason for that, every year the grasses leave behind all of the leaf material they made the year before. It's called thatch. Okay, and that thatch layer just kind of accumulates, and new grass grows out from underneath the thatch layer the next year. That thatch layer eventually gets broken down and adds organic material and builds up the A horizon. Okay, so that's why typically prairie soils are very good for agriculture. They have a nice thick topsoil that's got lots of nutrients in it, things like that. Okay, what we want to make sure of is that we preserve that A horizon and we don't allow it to blow away or wash away. Okay, that's soil erosion. It takes a long time to build soil. Okay, and so we don't want to lose it. We don't want to see it blowing away in huge dust clouds like they had in the Depression. Okay, which is why typically modern farming methods don't till the soil very much. Okay, we find that tilling the soil to open it up exposes it to erosion, whereas if we leave the plants from the previous year there, at least their roots, that holds the soil in place, and then we just drive the seeds in next to those plants, okay, and allow them to grow. Now, it does involve, of course, spraying the plants from the year before to make sure they're dead, otherwise they'll grow back and compete with that year's crop. Okay. All right, so typically if you see a hole in a prairie, you'll see a nice thick A horizon that slowly transfers to the B horizon, okay, where we've got kind of clay, and then below that you see kind of the sandstone kind of rocky layer below that. Okay, B horizon has very little organic material because it's too far down for organic material to end up there, except maybe the odd root that's managed to work its way down that far and die and decompose in there. Okay, typically it's very fine, so it packs really, really tight. Okay, and it's quite dense and hard to dig through. Okay, and so it typically has a very smooth appearance, whereas you can see topsoil, okay, which would be kind of up there, is much rougher. Okay, because it's more loose where this is tightly packed. Okay, so there's a lot of clay in the B horizon. Places like the tropical rainforest, surprisingly, have virtually no topsoil and almost all B horizon, because they're flooded most of the time and the topsoil typically just washes away. Okay? So they actually, the plants there actually pull their nutrients out of the floodwaters as opposed to out of the soil. The soil is just an anchoring point for them. Okay? And then the C horizon is made of parent material. Okay? This is a soil sample from kind of a foothills type of area, so near here. Okay? And we see that, yeah, we've got, you know, an A horizon that maybe runs to about, here. Okay, you can see that there's rock quite close to the surface in this soil sample. Okay, the B horizon, I should use a color you can actually see. Okay, the B horizon would run to maybe about there. Again, you can see there's quite a bit of rock in the B horizon, but it's a different color and it's more tightly packed. And then down below you see lots of parent material and rock. Okay, further down. Okay, the closer the surface the rock is, the younger the soil is. Okay, what happens to the Earth's, or the sun's energy, sorry, when it strikes the Earth? Okay, so incoming solar radiation, okay, let's say 7 million calories per square meter per day, okay, is what arrives at the Earth's atmosphere. All right, so we come in with 100%, okay, and we get a lot of absorption, okay, happening in the upper layers, about 16%. Meanwhile, in those upper layers, okay, we get scattering, okay, backscattering, that stuff that makes the sky blue. 6% of the light incoming is scattered, okay. 16% is absorbed there. Another 3% a little lower down absorbed by clouds, okay, so that's what we're looking at right here, okay. And then absorption by water and land, 51%, okay. Reflection, okay, we said backscattered there. Reflection by clouds, 20%, and reflected from the Earth's surface, 4%. Now, that's an average. Right now, here, what's this number? It's not 4%, it's really high, because what's the ground covered with out here? Snow. So this number is like 5%, and this number is much, much higher. Okay, they're going to flip-flop in the wintertime when we've got a bright reflective surface. Okay, that reflected stuff, okay, some of it is sensible heat, some of it is latent heat, which is something we're going to talk about. That's heat that's stored by water vapor. Okay, it takes energy to evaporate water, and when that water evaporates and moves somewhere else, when it condenses, it releases that energy. So it actually warms the area it goes to. All right. You're never going to need to know those percentages, kind of just the general mechanism. Okay? So the main input of energy into the global system is obviously the sun. Okay? Gravity plays virtually no part, okay, at least for heat. Okay? Magnetism, virtually no part. Okay? Geological forces, maybe. Okay? Certainly a volcanic eruption or something like that is going to put some sensible heat into the system, but not a lot compared to the sun. Okay? Gravity puts some mechanical energy into the system in the form of tides and things like that, but again, it's not something that turns into a lot of heat. Okay. Yeah, don't even need to worry necessarily about that. So I think I deleted that from your notes, didn't I? Or is it still there? You can just cross that part off. It's not important. Okay. We said the bulk of the energy on Earth is transferred within the atmosphere, so now we're going to look at how that happens. Okay? The main way that energy gets transferred in the Earth's atmosphere is by convection currents in the atmosphere. We call that wind. Okay? Convection currents happen because of the second law of thermodynamics. Energy has to flow from hot to cold. Okay? And it does that by moving matter, in this case air, from one place to another to carry that energy. Okay? All right, so they carry sensible heat. Sensible heat is exactly like it sounds. It's the heat we can feel. All right? You know, if we get a Chinook, it feels warmer, okay? Because it's bringing in warm air, and that makes it feel much more mild. Okay? Latent heat is that thing we talked about just a minute ago. Latent heat we don't feel, okay? But it's there. Okay? So if a whole bunch of warm, moist air manages to move up, okay, into our area from the south, okay, it's going to not necessarily feel warmer, but there's going to be this moisture in the air. And when that moisture precipitates and condenses out, it releases that latent heat to the new area, and then it becomes sensible heat. Right? A lot of energy worldwide gets moved this way. It's what you can see on the weather map. And if you ever watch the weather on the news, or you watch the videos on the Weather Network and they show, you know, these kind of clouds moving across, okay? Anytime you see a cloud moving into an area, it's bringing this, okay? Because clouds are made of water vapor, and it's going to be bringing some latent heat, right? When it's coldest around here, it's usually clear, right? It's those cruel days where you look out the window and, oh, look, it's bright and sunny, but it's 40 below, okay? It's 40 below because the air is clear and dry. Okay, and it's got no latent heat to try and raise the temperature up. We're not getting any moisture from anywhere else. Okay, everyone follow me there? Okay. All right, heat energy from the atmosphere can be transferred to soils and plants through conduction. Okay, so anywhere where they're actually in physical contact with each other, there will be some conduction, but it plays a very minor part. And we've talked about radiation all the way along, the absorption of energy from the sun. Okay, so conduction works this way. If I have a solid object, okay, and I heat up one end of it, the particles at this end will move around a lot, okay, or they'll try to, but they're very tightly packed. So they run into each other and they transfer that energy along, like the bucket brigade we talked about, down to this end. This is why you don't want to stir a pot of stew with a metal spoon, right? Because if you're standing there and you're stirring it with a metal spoon, eventually the metal spoon on the handle is going to get hot. That's why you use a wooden spoon for stuff like that. A wooden spoon doesn't conduct heat very well, whereas metal does. Okay, and we don't want that conduction to come up the handle and burn our hand. Okay, convection works like this: hot air rises, cool air descends. Okay, and we get kind of a movement of air. Right? Does it move very well on its own? In a global system, yes, where there's lots of air and there's no restrictions to its movement. In an enclosed space, it doesn't. All right. If you have a house that's more than one story, okay, so if you got a 2-story house in the summertime, where is it coolest? In the basement, okay, because your house is a small closed environment, and heat will go to the top, cold air will go to the bottom, okay, and you'll get this real temperature differential. If you want to equalize that, you got to turn your furnace fan on. Okay? And the furnace fan will force the air to circulate, and that will transfer the energy from the hot air above to the cool air down below, and it'll even out the temperature in your house. Okay, everyone follow me there? Okay, but in a big system like the entire Earth, that happens on its own naturally. Okay, the Earth has kind of its own fan. It's called wind. Okay, that happens on its own, but that doesn't happen within the walls of your house. Okay. Yeah. All right. Practical applications of this. Let's say I'm trapped in the woods. It's going to get really, really cold, and the only thing I have around are trees and snow. How am I going to stay alive? Dig into the snow, because snow is a good insulator. Okay? If the snow is of the right type, I might be able to just dig into it. Okay? What if the snow is really fine and I can't dig? As soon as I dig, it just collapses. What am I going to build then? Yep, I can use tree boughs and I can kind of pile them up and they can trap air on the inside. Has anyone ever built a Quincy? Okay, not that many of you. I used to do it in Lloydminster when I taught there because we had a snow ecology unit, okay, in Science 10 there. You never saw people could make a pile of snow so fast as when you put them outside in 30 below weather. Okay, so what I would have them do is build a Quincy. All a Quincy is you take a shovel and you make a pile of snow. Okay, you just shovel it all onto a pile, and the snow kind of naturally packs and cements itself together. You don't have to pack it yourself. You don't want to, in fact, because if you pack it, you force the air out of it, and the air is actually, the trapped air is what insulates. So you build this pile of snow, and then you hollow it out. Okay, you hollow it out, you get inside, and we would get it so hot inside with just people being inside that drips of water would fall on us from the snow that it was made out of. Okay, you could actually get it above zero inside, even though it was minus 30 outside. Okay, snow is a really good insulator, and it's white. So what is it doing to all your heat? It's reflecting it back on you. It's the perfect thing to use in an emergency to keep you warm. Odd, isn't it? Okay, that something that's cold could save your life, keep you from freezing to death. Okay, the reason it works so well is snow is just like fiberglass, the stuff that's inside your walls of your house. Okay. These things insulate because they prevent the movement of air. Okay? Fiberglass is exactly like it sounds. It's a whole bunch of really small glass fibers. And they're just kind of woven together randomly. And as a result, air gets trapped in the spaces between them. What can the air not do? It can't move. If it can't move, which of the heat transfer processes can't happen? Convection. Insulation prevents convection. Okay? Here's a wall of your house. Okay? If it's not insulated, the second law of thermodynamics will take the warm and put it to the cold. Okay? Because a convection current will happen. The air inside the wall will warm up and it will rise. And the cold air from this side will move in to replace it. And you'll get a convection current occurring within your wall that robs your home of energy. Okay, so what we do is we throw this in there, and it traps the air so that it can't move. If the air can't move, convection can't take place. Everyone follow me on that? Okay, snow works the same way. Because snowflakes can interlock and are very small, they create small little trapped air spaces between them. That air can't move, so snow acts as an insulator. And it's white, okay, so that it reflects your infrared heat back at you as well. Okay? Your heat waves come back. How many people have ever seen an emergency blanket? The ones that come in like a roadside kit. What are they made out of? Like the really cheap ones? They're really lightweight? Yeah, it's like a piece of foil. Okay? An emergency blanket is just like a big piece of foil. All right? And you put it around you, and make sure you put the shiny side toward you, not the dull side. The shiny side toward you, and it'll reflect your heat back on you. It doesn't do much for like preventing convection, but it does do a good job of reflecting your radiant energy back. Right? Tin foil. How many people have baked a potato with tin foil before? Okay? How do you wrap a potato with tin foil? Because there's a right way and there's a wrong way. Believe it or not. And I've seen people do it the wrong way lots of times, and it just astounds me. You guys ever notice that tin foil is different on each side? Shiny side and a dull side. Which side do you want facing in at the potato? The shiny side. Okay? The dull side absorbs the heat from the barbecue. It transfers it through into the potato. And as it travels through the potato, it hits the shiny side. And does what? Reflects back into the potato. You can cook a potato about 3 times faster if you wrap it the right way. Okay? But I've seen people who don't realize this, and they're just wrapping. They got half of them wrapped dull side out, half of them wrapped shiny side out because they don't realize there's a difference. And I just watch. I'm like, I want that one right there. The one that's got the dull side out because it's not going to be chewy. Okay? It's actually going to be cooked when you're done. Okay? Got to make sure you always wrap it the right way. That's using radiation. Okay? It's trapping the radiant energy. This traps convective energy. Okay? If you have a thermos, okay, like these, okay, they don't have any insulation inside, but they keep stuff warm for a long time. How do they do it? Okay, first off, yeah, it's shiny inside. Okay, so the inside is shiny metal, right? But what's in between the inner layer and the outer layer? A vacuum. Yeah, they actually, when they make these, they suck all the air out of it and seal it. So it's actually a vacuum. If there's no matter in there, can the energy transfer out? There's nothing to move, right? You can't get a convection current going, so it's a perfect insulator. A vacuum is one of the best ways to insulate something because it can't allow energy to move out. So you make it shiny to reflect the radiant energy, and you make it a vacuum to prevent convection. Okay? Seeing all these practical applications? What kind of question am I going to ask on your test about this? Probably something about devising a way to get something to warm up quickly or keep something cold or something like that. Okay, something about harnessing or preventing the 3 methods of heat transfer. All right. Okay, within the ocean, there's going to be energy transfers that go on within the ocean. Again, most of that's going to be by convection because the ocean is a fluid. Okay, ocean currents are a big part of that. Okay, if you've watched the weather recently, there's this big thing going on over by Iceland right now where there's this major warm air mass, ocean current, air current that's moving up towards the North Pole. We're getting the other end of it right now. That's why it's really cold here right now. Okay, but on the other side of the Earth right now, there's a whole bunch of really warm air rushing to the pole, and it's pushing all the polar air down to us. Okay, that ocean current, the North Atlantic current, is moving a bunch of warm water and air to the pole, and it's actually shrinking the polar ice at a rate 3 times its normal rate right now. Okay, and for the last few years, it's been shrinking quite fast, and they're really concerned that this year it's going to shrink an almost irrecoverable amount. Okay, we need to have a few cold years to allow that snowpack to grow again. Okay, after this event that's only going to last for about a week. Okay, they're saying as much ice could melt in this 1-week event as is melted in a couple of years, right? So you get these kind of convective things going on, and you can get a lot of heat transfer happening quickly. El Nino is another example of that. We're in an El Nino year. That's an ocean current that's bringing warm air to other places, okay, as well as warm seawater. Okay, the other place where hydrologic transfers can happen is this latent heat. That is water turning from one state to another. Okay? As energy is absorbed by the ocean, it turns some of the liquid water into water vapor. Okay? When it turns back into liquid water, condensing, okay, energy gets released. So you can see on this diagram here, okay, if we move this way, energy gets used to change the state. If we're going melting ice or we're evaporating water, we have to put energy in. But when that goes the other way, that is, water vapor condenses back to water, energy gets released, or liquid water freezes into ice, energy gets released. You can see that in the fall when we get our first real cold snap. It looks like there's a whole bunch of steam above the lakes and ponds and stuff like that. Okay? Clear sign that there's a lot of energy flowing out of the lake and into the atmosphere, and eventually that water is going to change state. Okay? And it always, of course, freezes from the top down. Okay? The surface at the surface that's closest to the cold air. Okay? All right. Okay, and then we said the lithosphere plays a very, very small part in transferring energy. It's good at absorbing it, providing energy for plants, things like that, but in terms of transferring it and creating global transfers, basically does nothing. Okay. All right. Whew, we got through that. Okay. Tomorrow, we're going to talk quickly about wind patterns, which will only take maybe about half an hour, and then we're going to start working on specific heat capacity, which is one of the two things that involves a tiny bit of very easy math in this unit. Okay, and then the next day we'll do latent heats. Friday, probably a little bit more about latent heats. Monday, we'll probably talk about biomes. Tuesday, finish everything up. Wednesday, review. Thursday, test. Okay, that's kind of where we're headed. All right, so it's coming to a head here pretty quick, guys.